the both areas are equal. So we know the rectangular area is length into breadth and the square is side into side. Suppose area of rectangle is equals to A1 is equals to length into breadth, and area A2 is equals to square side S into S. If both are equal, then we will be printing S, otherwise we'll be printing no. Rectangle A and B. C284. A1 is equals to 2 into 8 is 16. A2 is equals to 4 into 4 equals to 16. Both are equal. So it is S in 354. A1 is equals to length into breadth 3 into 5 is 15. A2 is equals to 4 into 4, 16. Both are not equal. A1 not equals to A2. So the output is no. Let's go to the coding part. C will be calculating, will be taking inputs A, B, C, length, breadth, and side of a square. A1 is equals to length into breadth, A2 is equals to C into C. If both are equal, then S, otherwise no. Am I clear? Okay, let's go to the next question. The next question is, we have to count the number of odd divisors and even divisors for a number n. Five test cases for one. For one, only one is the odd divisor and no even divisors. So, one odd divisor and zero even divisors. For two, one is the odd divisor and two is the even divisor. Two factors are for 4. Divisors are 1, 2, and 4. Odd divisors are 1, even 2. Because 2 and 4, two numbers are there. Am I clear? It is very easy. The coding part, see, we will be taking two counts, even count and odd count. We will be traversing through the loop from 1 to n. If it is an even number, we will be checking if it is divisible by n. Then it is even divisor. So we will be incrementing it. If it is odd number and is divisible by n, then it is odd count. Then after we'll be printing odd and even count. Am I clear? Any doubts? Any doubts? Hello? Okay, the remaining
No
questions.
doubt. No.
Okay, remaining questions will be taken by Samrita.
Okay, let's move to the third question then. First, we'll read the question. Can you see the screen? Okay. So here it's given check odd and even divisors. We will be given two integers a and b, and we want to check if there exists some positive integer n such that it has exactly a odd divisors and exactly b even divisors. Okay. Now see here, like you have 1 and 0, that means 1 odd divisor and 0 even divisor. Is there any number possible which has one odd divisor and zero even divisor? It is yes. Okay, n equal to 1 only satisfies that. Now let's go, means why is it working this way? We will understand. Okay, so hello, can you hear me?
Yes,
So during our JE days, we had read this formula about finding the number of prime factors a number has. So n can be means factorized in this way. Suppose 2 is also a prime number, right? And when we say even divisors, it means it has to contain 2. So suppose 2 occurs e times, and p1, p2, these are other prime divisors which we have up to pn, and this is a1, a2, like this up to an. So the number of total divisors that this number n has, it is e plus 1, a1 plus 1 up to an plus 1, right? Now we are given that there are a odd divisors and b even divisors. So that means we can easily conclude from here this fact, which will help us solve the problem, that a plus b is equal to this thing, right? Now what is b? B is the number of even divisors and a is the number of odd divisors. Okay, now so from here we can conclude one more thing, that e plus 1 times a will be equal to a plus b. Why? Because b is the number of odd divisors and this is the number of even divisors, and a is also the number of even divisors. So that means ea should equal b, which also means that b must be divisible by a. So that gives the entire crux of the logic over here. Now we will go to the coding section. Okay, see here. A is the number of odd divisors and B is the number of even divisors. If A is equal to 0, that means it will be no. Why? Because every number has 1 as its divisor and 1 is odd. So A cannot be equal to 0. That's why we are printing no here. Now if B divides A, that is B mod A equal to 0, then our answer will be yes. Otherwise we will print a no. Is this clear? Okay, good. Next, we'll move on to the next question. Again, first we'll read it out. Add permutation. Okay, did anyone attempt this? How did you do it?
Yes, the I attempt it.
Share your approach.
Here one, like, if we in array, if we take permutation from last numbers like 4321, it will give only one number if we add a plus I on all of them. So if we want to, like, add, like, if we want two numbers, two distinct number, then we can arrange it in such a way that like three places are adjacent and one is in another place, and in that way we can form this array.
My approach was also the same. Like first we'll print 1 till k minus 1, so that there will be k minus 1 unique numbers, and then we will print means n till k, so that there will be only single unique number. So k minus 1 plus 1 will be k unique numbers. And that was my approach to think
Okay,
of
okay.
6 and 3.
Yeah, yeah. Okay, okay. Got it. Good. So we'll discuss this for those who could not do it. Okay, first we'll start by looking at an example because that way it's most easy to understand it. Suppose we have this permutation 1, 2, 3, 4, 5, 6. Now I say k will be 3. That means I need three distinct set of numbers. Okay. Now I will just index them once. That will make it easier. Okay, these are the indexes in blue and we have the numbers in black. Now, whatever function we are given, if we apply this on it, we will get this 2, then 4, then 6. We are just adding the indices and the numbers on that index. This is 8, this is 10, and this is 12. Now, here we have again 6 distinct numbers, but we need 3. How do I do that? Since then observe one thing, if I reverse this permutation completely, like if I write 6, 5, 4, 3, 2, 1, then what will I get? Again applying the function, these are the indices and this is my array, then I will get 7, then 7, again 7, 7, 7, and then again 7. So what do you notice? If I reverse it completely, then all the numbers become same. That is, if k was equal to 1, then this would have been my answer, this particular permutation. But I have k equal to 3. That means I need two more distinct set of digits, right? So the intuition that we get from here is we are to reverse a particular subarray of the entire permutation. That will do the work for us, right? So let's do it again. 4, 5, 6. Since k equal to 3, I will say that I will reverse the only last three digits of the given permutation. Then I will get 6, 5, and 4. So this becomes 10, 10, and again 10. Now I will not do anything with the remaining n minus k digits of the permutation. So this becomes 2, then 4, then 6. So I get three distinct. You see, this is one, this is another, and this is another set. So I get three distinct digits. So this is from where we get the intuition of reversing only the last k elements of the permutation. So those k elements will form one set of numbers, and the rest will give distinct numbers accordingly. So I think that was all for the intuition. Now we'll go to the coding section. Did you understand it or any questions from here? No questions, right? Okay, let's go to the code. See over here, first we have taken the input, and then I have resized the vector to n plus 1 because I want 1 indexing, not 0 indexing. So here I have taken the permutation only, that is written that vi is I, that is for 1 will at 1 will have 1, at 2 will have 2, and so on. Next I'm reversing from v begin plus k to v end, means only the last k digits we are reversing because they will form the same set and the others will form the distinct sets. Now from 1 to n, I'm just printing it out, and that's it for the code. Okay? I think it's pretty much clear now. Okay, good. Next, we are going to the last question. Okay, first let us read the question properly. It needs understanding. Okay. You have a tree with n vertices. A tree is a connected undirected acyclic graph on n vertices with n minus 1 edges. Means all the nodes are connected to each other. Okay. Now you want to assign distinct labels to the vertices of the tree. You will choose a permutation p of the integers 0 to n minus 1 and then assign the vertex x a label of px. Now what is max? It is the minimum excluded integer. Okay. For a set S as the minimum non-negative integer not present in S. For this example which is given here, max of 1, 0, 2, 2, 4. Why is it 3? Because see, 0 is present, 1 is present, 2 is present, then 4 is present. So which is the number which is not present over here? It is 3, right? So the max, that is the minimum excluded non-negative integer in this set, is 3. Now let's go to the next example, max of 1. What is the non-negative integer not present in this set? It is 0. So max of 1 will be 0. Okay. Now define f of uv as max of this set px1, px2 up to pxk, where x1, x2 up to xk are the vertices on the unique simple path from u to v, including u and v themselves. So x1 is equal to u and xk is equal to v. So these are the nodes or the vertices of the tree, and we are labeling them, and this is the max of that. Okay, we need to minimize the max. See, it's given in next line. Defines code of the tree as this double summation of xy. Now this double summation simply means we are taking the sum of pairs of the nodes. Okay, sum of f means this function that we defined over here over all pairs of vertices. You must find the minimum possible value of score if you can suitably choose the permutation P. So we need to assign the permutation P such as to minimize this particular stuff over here. Okay. Now the input format is given. That we can discuss later. Let's go to the intuition part. Okay. first example, you will see the tree that is given there. It is 1, 2, 3, and 4. These are the vertices or the nodes, whatever you call them. Now you need to assign numbers like 0, 1, 2, 3. You have to label these nodes basically. So I can write 0, 1, 2, 3 like this way, or I can write 2, 0, 1, 3, whatever I feel like. Now, whatever we do, we need to minimize the function that was given to us. Now let's focus on the function that is given. Okay. See, I need to take pairs of nodes. If I take 1, 2, then 1, 3, then 1, 4, then 2, 3, 2, 4, 3, 4, 4, 1. Did I miss out anything? 3, 1. Okay, 1, 2, 1, 3, 1, 4, 2, 3, 2, 4, 3, 4, 4, 1. Okay. So in 1, 2, see in this particular subset, we have 1, 2. That is here the max will be 0, 2 is there. It will be 1. 1, 3. 1, 3. Here we have also put in the 1, 3 nodes this and this. It is 2, 1. So we are missing out on 0. In 1, 4, this node and this node, we have 2 and 3. We are missing out on 0 here also because 0 is not there in 2, 3. Similarly, in 2, 3, this nodes 0 and 1, we have 0, 1, so we will put here 2. Then 2, 4, we have 0, 3, we will put here 1. Then 3, 4, 1, 3 is present, 2 is not present, so it will be 2. 4 and 1, 2, 3 is present, 1 is not there, 0 is also not there, so it will be 0. Now you can see you will have to sum up these 1 plus 0, then 2, then 1, then again 2, then again 0. But this way it will not be minimized, right? This is just random. So we need to think of a way to minimize this max sum of all the pairs. Okay. So observe that if we put a 0 on the leaf nodes, like this is a leaf node over here and this is a leaf node. Now what is a leaf node? A leaf node is that vertex which does not have any children connected to it. Means it will have only one connection with its parent, like this and this are the leaf nodes over here. So if I put a 0 over here, all the paths crossing from the leaf node and above, that will not have 0 as the max, right? So we have minimized the number of paths that will have more than 0 as the max. And that is our goal. We need to minimize the total value of the function. So I will put a 0 on a leaf node. And where do I put the next one? Now, if you think closely, now let's take a bigger tree for understanding that. Now, I said that I will put a 0 on a leaf node. So, all the paths that is crossing from here, like this path, this one, whatever, this will have 0. So this cannot have 0 as its max because max is the minimum excluded non-negative number. Okay. Now where do I put 1? If I put 1 over here, then this path cannot have 0 and 1 both as its max. It may have 2 if it is not present in these paths. So if you think closely, you will realize that 1 should also be put in a leaf node because that will minimize the number of paths which will have more than 0 and 1 as its max. And that is what we need to do. Okay, so we will put 0 and 1 on the leaf nodes. Next, let's consider this kind of a tree. We said that we will put 0 and 1 on its leaf nodes. So in this path, I cannot have 0 or 1 as the max. Can I have 2? I can have 2 if it is not there in this path. So if I put 2 over here, then this path will have some other, means I will put 3, 4, all these numbers over here, right? So here the max will be n, and for all the other paths, it will be 1 or 0, means this path, this will contain 1. And here we already have 1, so I will have 0 in this path. So, uh, the final conclusion that we can make from here is that if we have a tree that has more than 3 leaf nodes, if there are more than 3 leaf nodes, then I can place 0 in one in one, and 2 in the other leaf, right? So only one path will be there, which will have n as, which will have, uh, okay, in 3 leaf nodes, then 0, 1, and 2 there are there. So n minus 1 plus 2 there will be the max value. That means this will be n plus 1. So if greater than or equal to 3 leaf nodes, we will have this as the max value. And if we have less than this, that is 2, or means less than 3 actually leaf nodes, then it will be 2n minus 1. Now why so? Because there will be one path which will have n as the max, right? And we already have n minus 1, because n minus 1 paths will have 1 as the max, and only one path has n as the max. So 2n minus 1 will be the value. Are you getting it, or is there any doubt? You can ask. Is there any doubt? Hello, am I audible? Okay, so you all got it right. Then we'll move to the code section. Okay, look here. First, we'll take input the graph. For this, we have defined this vector int j. This is basically the adjacency list. And here, first we have done g.clear, because for each of the test cases, we are using the same globally defined vector of vectors. So we will do g.clear first. Then we'll take an input the n, that is the number of leaf nodes that we wish to use it from one index. Then gi.clear. This means that whatever nodes are there attached to the particular node, we are first clearing it out, because of the same reason we are using the same g vector across the entire across all the test cases. Now, from 1 to n minus 1, because we just read here, it's written here also that for a tree with n vertices, we have n minus 1 edges. So for taking the input as edges, we did this. Now, why are we writing GA dot pushback GB and GB dot pushback A? Because it is undirected. Here it's written, it's undirected acyclic graph. So that means when A is connected to B, B is automatically connected to A. Now vector int leaves, because we need to store how many leaves are there in this tree. According to that, we have formulated the logic. So from 1 to n, we will check if gi dot size equal to 1, because during explanation also I told that for a node to be a leaf node, it has to be connected to only one parent, because it doesn't have any children of its own. That's why it is a leaf node. So leaves dot pushback I am pushing back that particular node. If leaves dot size is greater than or equal to 3, that means we have more than 3 leaf nodes. So we can assign one leaf node as 0, one leaf node as 1, and the other as 2. So our ultimate value of the function will be n plus 1. Otherwise, we can only put 0 and 1 on the leaf nodes, and there will always exist another part that will have n as the max. So it will be n minus 1 plus n, hence 2n minus 1. And that's it for the code. Any doubts, anyone?
Didi, is it necessary to use G vector globally?
No, it's not necessary. You can create it every time for each test case too.
Okay,
Uh-huh. Anyone else? No doubts then. Did you all understand it? Okay, great. We'll send the